Okay, so we will conclude this chapter, short chapter, by looking briefly at eddies and waves. So we looked at this figure before of the 500 millibar height averaged over the whole month of January in 2003. Obviously looks very smooth, except for a few wiggles here and there. And this is typical of a particular day. This is looking at 12 GMT on June 21 of 2003, and same kind of scale with 60-meter contour intervals and in decameters, so this is 5.88 kilometer height. Now you can see that suddenly there are lots of blobs and the waviness has increased. So the atmosphere is actually full of so-called eddies. Okay, eddies are these little circulating systems that are either clockwise or counterclockwise, so they are either have rising motion inside or sinking motion inside, and they get formed because of various processes in the atmospheric dynamics, which is basically non-linear. One of the main ones being is that the angular momentum as you go from the very large part of the Earth's surface around the equator to smaller regions towards the poles, right? As you go from the tropics to higher latitudes, you are heading towards the pole. The local radius becomes smaller and smaller, so the angular momentum conservation becomes an issue. So if you take a parcel of air on the equator, it has a certain angular momentum based on how fast it's moving on the equator, which is almost 1600 kilometer per hour. And as you go off towards higher latitudes, the tangential speed keeps dropping non-linearly because you are covering 24 hours, one circle in 24 hours. You have a much longer distance to cover near the equator than towards the higher latitudes, right? So nonetheless, with those kinds of details we'll look at. The circulation splits into these little eddies, and they are very common. And there are also these large-scale wavy patterns. Where do they come from? Again, without having done Coriolis, we have to just say it in words. As we said, Coriolis is zero on the equator, Coriolis effect. As soon as you step off, you begin to feel the rotational effect, and it keeps increasing towards the poles. And if you move from one latitude to another, you're carrying kind of the vorticity of that. Well, you are carrying the vorticity at that latitude to a different latitude where the vorticity is different because the rotational speed is different. You get a rotation induced into everything that moves at planetary scales because of the rotation. It's like standing on a merry-go-round. Even though you think you're going linearly round and round, when you get off, you begin to feel like you cannot maintain your balance because you've attained this dizziness because of the rotation, right? That's similar, the dizziness. Okay, so that vorticity change requires the air parcel to try to come back to its original latitude because the vorticity is different when it's pushed away. So then it overshoots and then goes back, so you end up with these waves. That's one of the ways to create waves. There are other ways where a heating of the atmosphere because of convection can generate waves as well. Okay, so there are all these eddies and waves in the system which make for specific features that you can see here. In the very first chapter when we started, we said we have these kind of tilting structures that go from lower latitudes to higher latitudes in both hemispheres. So this is a nice simulation from NASA about aerosol optical depth. Basically that means dust and pollution and sea salts and smoke from wildfires and so on that are being carried by the circulation. They act as tracers of the circulation, and you can see that they show these swirly features, which is what we called eddies, and they also show these wavy features, which are the various waves in the system. So we will learn a little bit about the waves because they are important and they play a critical role in weather and climate. So you can think of perturbations being generated in the system either because of heating or because of displacement, and that signal is dispersed out of the region of perturbation as waves. Okay, so atmosphere has these waves. It's like tying a rope and pulling it up and down, right? That's kind of what happens. So you have gravity as one restoring force, and you have vorticity, latitudinal dependence of vorticity as another restoring force. So perturbation and restoring force together make for waves, and the nonlinearities make for eddies and so on in the system. So we will learn those, but in the context of meridional circulation, it's important to see that, because when we average over time and average zonally or meridionally, things look smooth, but when you look at any instant or for a few hours, especially the satellite data, for example, things are never smooth. There are always eddies and waves in the system. Obviously, there are trade winds, but they are not always steady. There are also waves and eddies in these large-scale systems that we keep looking at as averaged meridional structures. All the physics that we derive by doing zonal average meridional sections is still valid. It's just that doesn't consider all the details of processes of eddies.